Problem number 8 from the Math 220 final review. So it says, without using matrix functions or a calculator, find the eigenvalues of the matrix and a basis for the eigenspace corresponding to each eigenvalue. Those will be eigenvectors. And graph the eigenspaces corresponding to each eigenvalue. Show the trajectory of the eigenvectors in each space. So in order to find the eigenvalues, we set a minus lambda I, the determinant rather, of a minus lambda I equal to 0. So, or in this case, b minus lambda I. So that would be 1 minus lambda times negative 5, and then negative 6 and 8 minus lambda. So that determinant will be the cross product 1 minus lambda times 8 minus lambda. Now 1 times 8 is 8. 1 times the opposite of lambda is negative 1 lambda. 8 times the opposite of lambda is negative 8 lambda, so that's negative 9 lambda plus lambda squared. Now we're going to subtract the product of this two, so that's going to be 30. That's equal to 0. So let's rearrange this and combine the like terms. That's lambda squared minus 9 lambda. And then 8 and negative 30 makes negative 22. Now this fortunately factors because I think, 2 and 11 will multiply to 22. And if the 11 is a negative and the 2 is a positive, we'll get a negative 9. So that's lambda minus 11 times lambda plus 2. So our eigenvalues are, of course, lambda equaling 11 for the first one. Lambda equal 2 will be our second. Negative 2 will be our second one. So that's an 11. So let's find our eigenspace corresponding to lambda equaling 11. So we go back and we take 1 minus 11, and negative 5, then negative 6 and 8 minus 11. And we know that an eigenspace is really just a special type of null space. So we we take b minus lambda I in this case. Remember, b minus lambda I times the any eigenvector should give you 0. That's how we find the eigenspace. So we get negative 9, minus 5, negative 6, and negative 3, 0. That's negative 10, not negative 3. I don't know what I was thinking. Okay. So, you can see these are multiples of each other. If I divide this by, let's divide this by 10, or negative 10, we'll get 1, 1/2, and 0. And then if we add 6 of these to this row, we'll get 0 there. 6 of these to this row, we should get 0 there, because we should get a free variable. And so there's our free variable, there's our pivot. So our x sub 2 is equal to x sub 2, it's free. And our x sub 1 is going to equal, if we subtract 1/2 from both sides, that's going to be negative 1/2 x sub 2. So our eigenvector basis is negative 1/2, 1. Now you could do any multiple of that will be an eigenvector as well. So you could say, well, that's negative 1 and 2 if you wanted. That's going to be the same thing. Or 1 and negative 2. But that's the basis for the eigenspace. Of course, the whole eigenspace is if you multiply x sub 2 times that. It's all multiples of that, which is just going to be a line. Now let's find the eigenspace for lambda equal negative 2. I'll just jot down here. This is for lambda equaling 11. Now for lambda equaling negative 2, we'll take b minus 2 times the identity matrix, right? And then we'll solve that homogeneous system. For that, finding the null space, which is an eigenspace in this case. So we get 1 minus 2 and 8 minus 2. So that should be negative 1, negative 5, negative 6, 6, And you can see clearly, whoa, something's wrong with that picture. Oh, it's a negative 2 is the eigenspace, not 2. So it's plus 2. So that should be minus negative 2. That should be a 3. I'll just scratch that out. That's going to be a 3, negative 5, and that's going to be a negative 6 and 10. That's more like it. Sorry, yeah. Lambda is equal to negative 2. So you can tell that these are not linearly dependent. They have to be linearly dependent in order to make an eigen when you subtract lambda I from the matrix. So this clearly is, if we add 2 of these to this, we'll get 3, negative 5, 0, and that'll be 0, 0, 0. And so that gives us x sub 2 again is free. So x sub 2 equals x sub 2. X sub 1 is equal to, now we'll add 5 and divide by 3. Right? Add 5x sub 2 and divide by 3. We get this equation. So we get 5/3 and 1. Now any multiple of that, really the eigenspace is that times x sub 2. So we could take we can multiply this by 3 if you wanted, and that would give us 5/3 if you'd rather. And that's a little easier to graph. So this is a basis for the eigenspace. That's a basis for the eigenspace. And I'm just gonna sketch this fairly quickly, actually. The eigenspace for lambda equaling 11 would be negative 1, 2. That would be through that vector, and all multiples of that vector, like negative 1/2, 1 will be in that, or negative 2, 4. You could go over 2 and up 4. So that eigenspace is going to be a line, basically, that contains, through the origin, of course, because 0, 0 is in every subspace, but also remember 0, 0 is not considered an eigenvector. And this is for lambda equaling 11. Now for lambda equaling negative 2, we get 5/3. Now, so we go 1, 2, 3, 4, 5, and up 1, 2, 3. That's right about there. And so this eigenspace for lambda equaling negative 2 goes this way. Lambda equals negative 2. Now, it says, graph the eigenspaces corresponding to each eigenvalue and show the trajectory of the eigenvectors in each space. Well, this is kind of interesting. Obviously, 11 is a repeller. It goes away from the origin. In other words, remember that if you take the matrix B and multiply it by any eigenvector, it's going to equal some corresponding eigenvalue times that vector. So if you take any vector on the eigenspace where lambda equals 11, it will be equivalent to just 11 times that vector. So that vector will go, if it's this far, it'll go 11 times the distance from the origin, whichever direction it's going. Now the peculiar thing is, when lambda is equal to negative 2, if you have a vector that's an eigenvector that's going in this direction, that's on the positive, the first quadrant, if you multiply it by negative 2, it's going to jump all the way over to this quadrant. So it'll still stay in the eigenspace, but it'll be twice as far from the origin as the first one. This was this far. It'll be double that distance, and it'll go back and forth on that eigenspace. But it's still repelling. It's getting further and further from the origin. So while I know the vector goes from here over to here and then back and forth as you multiply over and over by negative 2, it's still going to be going further and further from the origin. So we still say the origin is a repeller. And that's it.